So let's talk about acid and base ice tables. These are going to work with the definitions that we already have in order to fill them in. We're going to calculate pH from molarity and Ka. We'll calculate H plus and OH minus from molarity and Ka. And we'll calculate Ka or Kb from molarity and pH. You can also do it with pOH. So we're going to go into a bunch of different examples using the definitions for pH, pOH, Ka, Kb, Kw in order to fill in our ice table values.
All right, so we know this wouldn't be chemistry unless we tried to do some calculations with this. So let's calculate our equilibrium pH given a molarity and Ka. We're going to determine the pH of 0.025 molar solution with a Ka of 2.5 times 10 to the negative 4. So the first thing that we have to understand about this is that our Ka is going to give us the concentration of our H+. How? We're going to start with the general equation for acid dissociation, including the Ka definition. And then we're going to do an ice table. So we'll have HA, H+, and A-. We have left off H2O because it does not matter. It's equal to 1. So our initial concentration of HA is 0.025 molar, and H+ and A- are both going to be 0. So what is our change going to be? We're going to subtract X from HA. We're going to add X to H and A-. And so our equilibrium is 0.025 molar minus X. For HA, it's X for H+, and it's X for A-. Now we plug that into the Ka equation, and we're going to go fiddle with it in the next slide because we don't have enough space. So we'll start with what we had. We can consolidate those x's on the numerator to x squared, and we can use the multiplicative inverse, meaning we can multiply by the denominator on both sides, which will cancel out the denominator on the left, and it'll multiply on the right. Okay, so now x squared is equal to 2.5 times 10 to the negative 4 times 0.025 minus x. And if we distribute that 2.5 times 10 to the negative 4, we get that that's equal to 6.25 times 10 to the negative 6 minus 2.5 times 10 to the negative 4x. If we use the additive inverse, so if we subtract 6.25 times 10 to the negative 6 and we add 2.5 times 10 to the negative 4x to both sides, then we get x squared plus 2.5 times 10 to the negative 4x minus 6.25 times 10 to the negative 6 equals 0. We are not going to factor that shenanigan, and so we need to use the quadratic equation. It ends up being the plus, and our x is equal to 2.4 times 10 to the negative 3rd molar. I have every faith that you can figure out how to do that in your calculator. So I'm just kind of skipping over how to plug and chug here. But that gives us the H+ concentration, because if you remember back in our ACE table in the previous slide, our concentration for H+ and for A- was X. Well, we're looking for pH, so we take the negative log of the H+, and we get 3.62. Now, I should note, we have 2 sig figs in 2.4 times 10 to the negative 3rd, and we have 2 sig figs in 3.62. And you're wait, what? Why? What is this? We have to remember that we only count the digits after the decimal as significant figures once we've taken a log. So that 3, that's order of magnitude. It does not count towards sig figs. The 6.2 is what counts. So we have 2 sig figs going in, and we have 2 sig figs going out. Even though it looks like 3, it's actually 2 because we took a log. Yes, I know that's going to be hard to remember, but do your best. All right, so what if we wanted to determine Ka or Kb from molarity and pH? Let's give it a whirl. What are the Ka and Kb of a 0.756 molar acid with a pH of 2.68? Generic acid, so we're going to use the generic equation. And we know that our H plus is going to be equal to our A minus since we have to dissociate that acid. So our pH is 2.68 and 10 to the negative 2.68 is the concentration of the H plus and the A minus, which is 2.1 times 10 to the negative third. Now we're going to use that general equation for an acid dissociating, and we're going to apply an ice table here. So we have 0.756 molar, and then we're going to add the 2.1 times 10 to the negative third to the H and the A minus, and we're going to subtract it from the HA. So if we go ahead and do that math and plug it into Ka, we have 2.1 times 10 to the negative third squared over 0.756 minus 2.1 times 10 to the negative third, which gives us a Ka of 5.8 times 10 to the negative sixth. If we want to find the Kb, we can then set up the Kw equals Ka times Kb equation and solve for Kb, which is 1.7 times 10 to the negative 9. Not so bad, eh? All right, let's try another. All right, so let's try another one. We're going to determine H plus and OH minus from molarity and Ka. Determine the pH and OH minus concentration from 0.276 molar benzoic acid with a Ka of 6.3 times 10 to the negative 5. So we write our equilibrium equation. Benzoic acid plus water becomes C6H5COO minus plus hydronium ion, and then we write our Ka. It's equal to H plus times C6H5COO minus over benzoic acid. We're now going to apply an ice table. So we know that we start with 0.276 benzoic acid, and we know that we're going to subtract off a certain amount X that dissociates. So if we do that, we end up adding H plus and adding C6H5COO. We can plug that back into our Ka, so that we have Ka is equal to X squared over 0.276 minus X is equal to 6.3 times 10 to the negative 5. All right, so let's go on a little journey with this information. We can solve for X. We can simplify the top to be X squared, and on the bottom, we're going to multiply by the multiplicative inverse. So we get X squared is equal to negative 6.3 times 10 to the negative 5 plus 1.8 times 10 to the negative 5. If we then use the additive inverse, we get X squared plus 6.3 times 10 to the negative 5 minus 1.8 times 10 to the negative 5 is equal to 0. At this point, we realize we're not going to be able to factor that. We use the quadratic equation, and we find that X is equal to 4.2 times 10 to the negative third. That is the H plus concentration. Because remember, we started with the Ka. Now, let's try this a different way. What if we approximate 0.276 minus X to be 0.276? And you're wondering, why can I do that? Because our Ka is times 10 to the negative fifth, and that's kind of tiny. So we suspect that it will do absolutely nothing to the concentration of our acid. So if we do that simplification, X squared over 0.276 is equal to 6.3 times 10 to the negative fifth. We multiply by 0.276, we take the square root, and X is equal to 4.2 times 10 to the negative third molar H plus. Lo and behold, we came out with the same answer. But that second one, that second version was a lot easier to do. We did not have to use the quadratic formula. And the quadratic formula, kind of a pain in the ass. You're likely to make lots of mistakes. So if you can find an approximation that is valid and will give you the same answer, use it. Okay, so we know that option 2 is easier. If you do molarity minus Ka and it equals molarity still, you can safely use this estimate. The way that they put it in the book is that when X from the shortcut over molarity is less than 0.05, it's a valid assumption. So if your value will only change by less than 5%, it's okay to do this estimation. All right, so let's try another one. Again, we're going to determine H plus and OH minus from molarity and Ka. This is actually still the same one. We haven't finished the problem. Sorry. So we have an H+ concentration. That's what we determined, but we needed an OH- and we needed the pH. So from the previous slide, our concentration of H+ is 4.2 times 10 to the negative third molar H+. And if we take the negative log of that, we get the pH, which is 2.38. Now, we have two options at this point on how to get to OH-. We can do 14 minus 2.38 and get the POH, and then do 10 to the negative POH and get OH- concentration. Or we can take our H+ concentration and use our KW equation. I choose to do KW this time. And I find that my OH concentration is 2.4 times 10 to the negative 12. Now, if I take the negative log of that, I get 11.62 is the POH. Now, I want to confirm that if I went the other path, I would get the same thing. So I'm going to calculate what the POH would be if I did 14 minus 2.38. And lo and behold, it also comes out with 11.62. So I can actually do more than one path to the correct answer on these types of problems. In fact, a lot of these types of problems. So as long as you actually do your math correctly, you will get full credit if you get to the correct answer. You may lose points for making algebra mistakes or pushing the wrong numbers in your calculator or rounding errors, but you will not lose points for going a different path than what I have shown, because both are equally valid. All right, we're going to calculate values from Kb and molarity. So let's say we want to determine the pH, the POH, and the OH- concentration of 0.350 molar cyanide, which is Cn-, with a Ka of 6.2 times 10 to the negative 10th. Well, Ka is defined for using an acid, but Cn- is base. So we're going to go ahead and use Kb and set up the Kb equation. So we have a Ka. We can find the Kb by using the Kw. And I'm not going to show you how to do that again because we've already done it multiple times, but we get 1.6 times 10 to the negative 5th. At that point, we set up the equation for how Cn with water is making OH-. Cool. We got the thing. Now we're going to set up an ice table. So we have 0.35 molar cyanide. We start with 0 hydrogen cyanide and 0 OH-. We subtract from the Cn- and we add to the HCN and OH-. Now we're going to put it into the Kb equation. Okay, so we've got our chart from the previous slide. We plug it into the Kb, and we get x squared over 0.35 minus x. But I'm going to assume that that's approximately equal to 0.35. And so I solve for x, and I get 2.8 times 10 to the negative 3rd molar OH-. Then I go ahead and I check to see if my assumption was okay. So I got 2.8 times 10 to the negative 3rd molar OH-. I put it over my original molarity. I multiply by 100, and I get 0.8%, which is decidedly less than 5%. So okay, we can use that assumption. So at this point, we know the OH- concentration, which means that it's a very short putt to POH. Negative log of that concentration is 2.62. And we can get pH by doing 14 minus 2.62, which is 11.38.
You must do an ice table for weak acids and bases. There's no way around it. If you have a weak acid or a weak base, you will be doing an ice table. You're going to use the definitions of Kw, Ka, Kb, pH, and POH to find relevant values for said ice tables. And when Ka or Kb is tiny, you can assume that the plus or minus in x in the denominator does not matter. And that's if you're doing plus or minus 2x, 5x, whatever. After the math, the concentration will be approximately the same. And you can check that assumption. So if the x that you come up with when you make that assumption divided by the concentration of reactant times 100 is less than 5%, then your assumption is valid.